Thank you. Hello, everyone. Good morning. My name is Ranalter, and I'm going to present joint work with my supervisor, Cezary Kaliszyk, Florian Rabe, who's also present, and Geoff Sutcliffe. And I'm going to be talking about the dependently typed higher order form for the TPTP world as well. I'm going to start off by giving a very quick and brief introduction to higher order logic, which most of you probably know already, but we have a few quirks in our presentation that are worth mentioning. Then I will motivate why we are actually going beyond that, and then introduce dependently typed higher order logic. And this is not exactly new. This was introduced by Florian, who's also present in 2023. But I think it's good to have a solid base so I can tell you more about the TPTP integration and also as kind of a foundation for the later talk by Colin himself. Then we'll talk about the TPTP integration and conclude. So, high order logic, something not very new or exciting, but very stable. So, our presentation of Rabe has a theory, a context, it has types and terms. In the theory, we can find base type declarations, which are just simple types. And we can have constant set of types, and this F we can see is basically just formulas. So that's not something we can find in the DNF here, but it's standing for Boolean valued terms. Our context is just context as we are used to. And in our types, we see this O, which represents the Boolean terms. So higher order logic, we have this simple type theory a la Church, which is classical with base type for Booleans. And we also have implication, which is a bit maybe surprising because the usual connective and quantifiers can all be encoded or written without using implication as a base or a primitive connective, but we will need this later on for decode. And the other thing is that we have equality, and this equality is types. With this, we can then write statements down like the one down here for our functions from maps to maps to maps. We have equal expansion, a primitive rule in decode, so this is just a very simple thing. We can make judgments about these things. The more interesting for higher logic are, of course, that we can prove something. And I am omitting subscript capital T in the provability relation grid, which is better theory would be. But it's getting covered otherwise. So we have provability of well-formed Boolean terms, and we have typing judgment. So we can say a certain term, a certain type, we can prove that. And there are also two more judgments, which are not very exciting in Booleans. For one, this is that two types are equal, and in Boolean this is just equality, it's just the same thing. And the other thing is that a type is well formed, and this is in Boolean just it appears somewhere in our theory and we can look it up. But once again, these things will be interesting once we get to decode. A very small example, we can then encode the natural numbers in our theory by saying, okay, we have a type of natural numbers, we have constants, 0, the successor function, plus, very simple, defining equations for successor of plus. And then we can make judgments. For example, we can prove that plus is associative, or that the successor of plus 0, successor 1 is a natural number. This would be easy to show. Okay, so we all know this. This is a perfectly good system. Why should we break it? Well, let's look at the reasoning by it currently. On the one hand, we have this automated reasoning thing with the TPTP, so 1,000 problems of theorem proving, this whole world and infrastructure that enables the communication and this between systems with the great the CASC with the competition where theorem proving systems can go against each other at this language. And this side of the world started very simple. We had CMFs and we had first order logic, and with the power and time we kind of grew in abstractedness and started to add things. Suddenly we had type first order logic, and then we had higher order logic, and then we got polymorphism. So we are seeing there's kind of a trend for more expressivity, even if that means that things get harder. On the other end of the spectrum, we have interactive theorem proving, which has very complex type systems, such as dependent types and other nice things. But we also see that in the IGP world, we are growing towards automation with hammer systems. And our idea for Devo is kind of build a little bit of a bridge between those things. So we want to be able to close the gap between those things. And with that motivation, let's take a look at what Devo looks. This is just a whole presentation from before where I marked the interesting parts. So we're looking at the types. Now we want to have dependent types. So we no longer have just simple types in our theory. We no longer just have simple types as a possibility for our types or simple function types, but we replace them with the more general dependent variants. So now we have this type A may depend on a term X of type capital A in our theory, and we can have arbitrarily many of those. We have in our type hierarchy, or in our types now, as the type hierarchy, is thing where we can apply terms to our types. And we have that our function types may now depend on terms. So this type of B, the resulting function type, may have a dependency on X. To show a bit more about how this looks like, or what effect this has on the system, I have here 4 rules from our method reduction calculus for work, which are all very simple. We have the typing of implication, we have the implication proof rule, we have congruence for function types, and we have type reflexivity, which is a bit a misnomer. It's actually type equality, but in Go that's just reflexivity. So here they're the same. And if you look at the typing of the implication, what changes now is that we have an S on the right-hand side. So if you want to see that T is of type Boolean, we might already need to account for things that happened in the S. And this is why we have implication now as a primitive, because our connectives are no longer, our connectives have now a dependency, which can be seen here. For the proof rule, nothing changes. We already have that S is a prerequisite to show T. So in the proving itself, there is no change. However, in the congruence, of course, we now don't have only simple function types, but we have dependent function types. Once again, we see that we use this X of type A in our context to maybe prove that B is equal to B prime. The big change, however, is in the type equality. So previously, I said it was very simple. It's just the same thing. But this thing kind of explodes when we add dependent types, especially because our logic is extension. So we see here that now type equality of two type of two instantiated types A, one time with terms S1 to Sn and one time with T1 to Tn. Now, first needs to check that A is a type in our context or in our theory pattern, which has the appropriate number of arguments. So this is the same as previously. But also, we need to see that each of the arguments are equal. So now our type equality reflects into term equality. Our type equality requires actual proving effort. And with that, typing or typeness is not trivial anymore. It might be undecidedly. We think, however, that this is a fine price to pay, given that in our experience and looking at things, on the one hand, often it is the case that typing, the well typing is easier to prove than the actual statement. The statement is, if you're improving in general, it's undecidable anyway. So just having this in as an additional is, of course, a bit icky, but it's also not as bad maybe as one might think, and it's worth to reinvestigate it. So we think this is time for us to pay for this. As a small example, I used a favorite example of every person who said the best dependent type ever, lists of text length. We now have in our types, in our theory, a type of list that takes as arguments an FR number. This is either, you can either write it like this with the time notation, or you can just say it goes from next to type. This is a taste thing. And then we have constants, where nil is the empty list, and we see we have here the type list, and we apply to it 0 as an argument. We also have cons and application. These look like expected, but here we see already that in application, the append function, we have that the list now has this plus in it, in the type. So we now have this, already see this period grouping aspect of typing. And then we can make judgments. For example, this judgment down here, where we say that appending the empty list to anything is just anything back. And we also see here that in the formation like we have it, we don't use inference of terms, we just list everything as arguments. So application takes 0, 1, 10 as arguments, which are the natural numbers which instantiate our lists. And we keep them, we don't throw them away. Right. The other thing which makes eval very cool is that there is an erasure. So eval itself is not very widely supported yet, but we're getting there. And to increase the usability of this, there is this dependency erasure, which uses partial equivalence relations to capture the information that is lost during erasure, during this cancellation. And partial equivalence relation, of course, is equivalence relation that thus isn't reflexive. And it works like this. I only give 2 cases to give you kind of a feeling for it. On the one hand, we have this case where we have a type declaration of theory, and if we erase that, we get 3 things. For one, we get just the erase type, so a simple type A without any arguments and any dependencies. Then we get this A star, where the star denotes the partial equivalence relation. So we now have this predicate A star, which depends on all the types of the arguments, and then it takes 2 instances of the term of this type. And this is important because otherwise you wouldn't be able to relate functions to each other with the partial equivalence relation. And so basically the idea of A star is a term A belongs to the original dependent type if this predicate which takes the arguments of the dependent type into it's a velocity. We can see this here when we reverse the term of some type, we get the statement A star XX in our context, telling us okay, X is originally of this dependent type A. And the third thing, or the set of third things we get is just a set of axioms in our context that establish that this A star actually behaves like a partial equivalence relation. And for a type or a term of some type, we get, of course, that the term is of now the erase type. Right. This is the erasure in very short. And now we get to the interesting new things, which for one is the new TPTP dialog. So again, TPTP, the Thousand Problem Coherent Program, is a very successful infrastructure enabling systems to be compared. It also has as part of this infrastructure, this TPTP doors, a number of languages of dialects. And I've illustrated this with this explicitly comic book. Nevertheless, logicians make new languages because we make more languages. That's it is where you have so it's the power of failure is complete. Let's go meet dogs. Hi dogs, how nice. Oh wow, nice dog. You did a great job. I'm so proud. Thanks. I'm going to give you a reward. What do you look like? What do you like about the world? Birds are pretty cool. No, wait. Great, I'm going, and here the little thing is saying, great, I'm going to give you lots of languages to study, each with its own phonology, word ordering, morphosyntactic alignment. And the linguists of course very excited. And so we are in the same position, we're very excited about this dialect of TPTP we introduced, so we can start to make this more widely used and study it and can work with it. And with the same idea, we are going to introduce this THF dialect, which is very similar to THF, the typed higher order form, because THF already allows a dependence of types, but not on terms, but on other types. It's just polymorphism. We have, for example, that we can have a polymorphic list, which takes as an argument a type and returns another type. Then we can have, for example, an instance of this, which is the list of natural numbers, netlist, where we apply this to the natural numbers. And the const operation just is then under this parameter or every type, and then we get an argument of this, give a list with a matching type and get a list of this type. And given that this infrastructure was already there, it's sensible to just take that and adjust it so that systems can easily extend the path that we work with this. So we took this and just changed that we now also depend on other concrete types, not on type variables. So in DHF, the determinant type higher order form, we now have that, for example, a list might also take a natural number. That the empty list also uses application operator X, and instead of using a type as argument, we have terms of a certain type as argument. And the binder, instead of just taking type variables, now takes number variables. So this extension doesn't break anything, doesn't require anything to change in the previous version of DHF. It's just a bit more. To illustrate this, I have here a very small example where we do kind of a step-by-step transformation of keyboard statement into DHF. So this is just something you have seen on the slides previously. This is the definition of append. We have two natural numbers, n and n. We take the list of length n and the list of length n, and we get the list of plus nn. The first thing is obviously the declaration of this app, but that doesn't really change. The DHF is just app. I'm using here the monospace to illustrate the difference between mathematical notation and the DHF notation. The next thing we both have in TPTP with app is this pi, this notion of pi with the dots as a primer. And we change this, as we have seen previously, with the already existing potential arc. The argument list m and m of type nut is then extended to this, where we use capital letters, and we cannot concatenate the variables itself, but we need to list them themselves. Function types errors are just written as these number errors, and the last change we need to make is that the application of an argument to a type uses the x. So this is then the complete transformation of keyboard and mathematical notation to DHF. I have a second example, which I won't go into detail about everything, because most of the things we have just seen, for example, the applications of here, and instead of the for, we have the exclamation mark that the TH option already has. But I will focus on three minor things. So one, usually we have this notion of the context of when we prove something. The other thing I will focus on is, again, these additional arguments here. I already mentioned we don't throw them away in keyboard, and the type equality. And if we translate this to DHF, what happens is that, for example, for once the gamma goes away, the complex, the theory is just the rest of the problem. We keep the inferable arguments because the TPTP makes a point to not prescribe any kind of logic to it, so it wants to keep all information as possible. However, we throw away the typing of the equality. This is a bit annoying because in type checking that requires us in a way to infer the types of both sides of the equality and check if they are equal, which is additional work. In PTP, the BNF, the language BNF, in principle specifies a form of typed equality. However, as my experience goes, nobody uses this. I have not yet found a single parser that actually is able to pass typed equality. So we decided to go with the untyped equality in DHF, which requires a bit more work when type checking. What else do we have? We have some kind of supporting infrastructure here. It doesn't just to have a language and do nothing with it. So on the one hand, we have dlash, which is an extension of lash, which itself is a support of satellites, which is the currently only proper real pure native keyboard prover. We have the well-extended Leo Freeze logic embedding tool, so that we can auto type checking. So it generates type checking constraints that might, again, those again written in then THF, as well as the erasure of DHF to THF. So we can just predict DHF programs and generate things that a wider array of groups can work with. There is the MMT keyboard implementation, which is mainly used for developing formalizations and was extensively used in the original paper. And we also have the TPTP write support in the form of TPTP4X, which pretty prints DHF programs. We have the BMF parser, which generates a syntax tree. And of course, system on TPTP has a own proof of variant, which is basically just translating a DHF program into THF and then giving it to my file. And the other nice things we are used of in TPTP, the TPTP write. Right. So in conclusion, I have introduced to you dhole as an extension of code with dependent types, a classical extensional logic, which is very cool and very neat to reason with. Reasoning is intuitive, exactly due to these reasons. And as a downside, we now have to live with undecidable type checking. That might be difficult, but we're in it. DHF is the corresponding integration of dhole into TPTP. We already have over 150 problems, I think, in this new dialect. And with this, we hope to stimulate research into dependency types, higher order logic, and get closer together so we can all live together in harmony. And with that, I thank you for your attention.